Good afternoon. This is Professor Shannon Gracie. We are in section 2.5 from Sullivan and Sullivan's text entitled titled Precalculus Enhanced with Graphing Utilities. So today we're going to be discussing graphing techniques using transformations. So this is the stuff we'll be learning. We'll go ahead and get started. So we'll just do the warm-up together. What we'll be doing today is we're going to be graphing these on the same screen and comparing how they change using both the graph and the table. So let's do it. Go ahead and grab your graphing calculator. We're going to get to the y equals screen. And the first graph will be x cubed. That's our library function. So we're going to compare how these other two change, comparing it to that original. So the second one, we're adding 4 to each function value. And the third one, we are subtracting 4. So let's check it out. Okay. So if we take our screenshot here, oops, make this a little bigger. Okay, so in black, I'll do the original. So the original graph looks like that. So that's our y1 equals x cubed. And then if we do our y2 graph, whoops, looks something like this. Oh, I don't like that one. Hold on one second. Trace that one better. So y2 is x cubed plus 4. And then in green, we'll do this guy here. And so we have these 3 graphs. So I think you can see what's happening here. If you just look at x as 0, you've got an ordered pair on the black graph at 0, 0. You have an ordered pair at 0, 4 on the blue graph, and at 0, negative 4 on the green graph. But you can compare using a table of values as well on your calculator. And so we'll compare each of y2 and y3 to y1. So if you go to table, it's going to show y1 and y2 and your x value, right? So the change in x is a half. And so here we are. And then in order for us to see the comparison between y1 and y3, let's go ahead and go to our y equals, and we'll take this guy off. If you go to the equals and hit enter so that it's not highlighted anymore, that graph won't show up. So you'll just have the 2 graphs. And then if we go to our table feature, we can compare y1 to y3. So let's check it out. Okay, so if you notice here, so if you notice with the first one, each of the y values on y2 are 4 greater than the y values on the original library function. And over here, when we were subtracting 4, each of the y values is 4 less than the y values on the library function. So let's talk about what happened. Describe y2 in terms of y1. Well, the graph of y2 is the graph of y1 shifted up by 4 units. And how about the y3 in terms of y1? Good. The graph of y3 is the graph of y1 shifted down by 4 units. So, once you memorize the library functions, it's very easy to graph functions that have been a library function that has been transformed in some way by understanding these relationships. Okay, so now let's look at, something a little bit different. We still have, a subtraction by 4 and addition by 4, but look what happens. It's inside what's being cubed. So let's go and we'll change our y equals, and now we have to do, so we basically have to do the quantity x, oops, I'm sorry, we can keep that first one the same. So let me clear this. The first one is still going to be x cubed. But our second one will be the quantity x minus 4 cubed. And then we have down here the quantity x plus 4 is being cubed. So let's see how this changes our graph. So there's the original. So now instead of going up or down, do you see they're going left and right? Okay, exciting stuff, right? So here we are. Here's our picture. Okay, so again, this one here in the black is our y1 is equal to x cubed. And then in the blue, we have our second one. That was when we subtracted 4. So that ended up shifting it 4 to the right. So y2 is x minus 4, the quantity cubed. And our third one here, y3, that was a shift to the left. So y3 is x plus 4, the quantity cubed. So now when we have our table of values, let's check out what's happening. So if we go to our table, nope, sorry. Yes, I did that right. So if you look here, what's happening for y2 and y1, so let's think about what's happening here. When x is 0, your original graph is 0, but y2 ends up being negative 64 because you're cubing 4. So actually, one thing we might want to do is we may want to go to, let's delete this one. Let's do a different start to our table so that we get a better look at what's happening. So we'll go to table setup. The table start we're going to say is negative 4. Nope. I want to go here. I want to go to -4. The change in table, let's just do 1. And then we'll see what this guy looks like. So now if we go to second table, there we go. This will give us a little bit better basis for comparison, except you're still not going to see where the 64s line up. So one more time, we're going to do our change in table larger. So the change in the table, let's do 2 and then graph. Nope. Second table. There we go. Okay, I believe this will take us where we want to go. All right. So here we are. So if you look here at our table, so when x is -4, your original graph would be at -64. Your second graph is going to be -512. But if you look, I'm looking for the things that correspond. So when x is 0, the original library function is 0. Now here, when x is 4, right? Do you see that is when your y value is 0 for your other ones. So basically, we shifted 4 to the right in order to get our 0 graph. So if you look at the blue graph, do you see that at x equal to 1, 2, 3, 4, you get a 0 on our y graph, whereas when you're at 4 for the original, it's going to be way up here. All right. All right, so let's do the same for our y1 and y3. So again, I'm going to go to my y equals, and I'm going to take this one off, and then go to our table so that we can look here and what happens. So here we get our 0 when x is -4. And so that means a shift to the left of 4 is what gets you your intercept, your x-intercept. Okay, so here we go. Describe y2 in terms of y1. So the graph of y2 is the graph of y1 shifted 4 units to the right. And then y3 in terms of y1, the graph of y3 is the graph of y1 shifted 4 units to the left. Okay, so we've talked about vertical shifts and horizontal shifts. So now let's take a look at if you've got a multiplier to the function. So a new set of functions. So our first, if we go to our y equals, we now have x to the 4th is our regular graph. And then this is going to be, let me just clear this. It'll be 2 times x to the 4th. And this one will be 1/2 times x raised to the 4th. So let's check it out. That's the original graph. Okay, so they all look pretty close in. Let's try zooming in and see what that gets us. First graph, second graph, third graph. Now I'm going to adjust the window because we don't need, we can start the y's at like -1/2. Let's do that. And let's do our y max at, I don't know, 10. Let's see what this looks like. There we go. That's looking good. All right. Okay. So here's the picture of our graphs. So we've got our original graph is in the middle here. We'll do it in the black. And then, so that's y1 is x to the 4th. And then this is what happened when we multiplied by 2. So each y value was multiplied by 2. So we ended up getting a narrower graph. And then this guy, when we multiplied by 1/2, do you see that it gave a wider graph? So what happened is we had a vertical stretch for the blue graph and a vertical compression for the green graph. Times x to the 4th. Okay, so if we create a table of values, we would have we can, let's see. Oh, that's okay. That would be our original and our y2. That's fine. Those values are fine. Okay. So as you see, y1 and y2, so y2 is each of these y1 values doubled. So it ends up stretching our graph vertically. And then if we go to our y equals, and if we look at just y1 and y3, now if you take a look, you'll see that each of the y values from the original y is x to the 4th has been multiplied by 1/2 or divided by 2. So describe y2 in terms of y1. Well, y2, actually the graph of y2 is the graph of y1 stretched vertically by a factor of 2. And then the graph of y3 is the graph of y1 compressed vertically by a factor of 1/2. All right, so next up, let's just do these two. So we've got the same first graph in our y equals, and then clear these out. Our second one is just doing negative x to the 4th. And then I want to adjust the window a bit to be -10 on the y, so we can see the whole thing. So that's our original, and that is the other graph. Okay. So our original graph is here in the black. So that's y1 is equal to x to the 4th. And then our second graph, basically apply everything that was positive. Whoops. Everything that was positive becomes negative. So you have y2 is negative x to the 4th. So if we look at our table of values for y1 and y2, we will have, you see how the y values are opposites? They're negatives of each other. And what happened, I mean, when this graph, if we're looking at y1 and y2, the graph of y2, think of it as a reflection. It was reflected about the x-axis, right? The x-axis. So here we go. The graph of y2 is the graph of y1 reflected about the x-axis. Okay. All right, so another couple of functions here. Square root function. So let's check out what happens here. So second square root x, and then second square root negative x. Make sure you're using the negative symbol and not the subtraction symbol. So let's go ahead and zoom standard. Let's see what happens if we do a standard zoom. There we go. That's a better picture. All right, kind of cool. So the original initial graph is this guy. And then the second graph is this one here. That's not very good. Okay, so y2 was the square root of the opposite of x, and y1 is the square root of x. So creating a table of values for y1 and y2, This one will be a little odd. If we go to second table, actually, it's kind of interesting because let's change the setup on the table. Oops, second table set. So let's start the table at -4 is fine to start. Let's have the change in table be 1. Let's see what that looks like. Second table. That'll get us what we need. Okay, so let's copy this. And then so what we have going on for the original graph, you may have noticed that the domain starts at 0, so you're not going to get a real number solution. That's why it says error. So look at what's happening. At 0 you get the same value, but what's going on is when you have that negative on the inside, it's making a shift on the x values. So y2 is going to have outputs when you enter in negative values for x, whereas y1 will have outputs when you enter in positive values for x. So let's take a look at the graph itself and see what happened. This graph basically, the blue graph is that black graph which has been reflected about the y-axis. So let's go ahead and write that in. So the graph of y2 is the graph of y1 reflected about the y-axis. So when the negative is inside the function, you reflect it across the y-axis. When the negative is applied after the function is found, you reflect it across the x-axis. Okay, so here's a summary. We did a lot of exploration here because in my experience, people have some issues sometimes with the stuff. So I thought it was worth the time spent. So here we go. Here's all the stuff we did in general. So this was like our first warm-up. So for vertical shifts, you raise the graph of f by k units. So basically you add k to your function value, each function value. And conversely, if you're subtracting, you lower the graph of f by k units. So you subtract k from f of x. So each y value you would subtract k. Horizontal shift, right? So you shift. When you have an addition inside, you shift the graph of f to the left by h units. And what's happening with the functional change is you replace x by x plus h. And over here you would shift the graph of f to the right h units. And again, you'd be replacing x by x minus h, compressing or stretching. So if you have a multiplier to the function value, you multiply each y coordinate. Of y equals f of x by your a. So the functional change is multiply f of x by a. Now, as we noticed with that graph of x to the fourth, we had multiplied it by 2 and then by 1/2. So what happens is if a is greater than 1, you stretch the graph of f vertically. Now, if you've got, a proper fraction, right? You've got a between 0 and 1, you're going to be compressing. So you compress the graph vertically. Now, if the multiplier is inside the function, not outside, then it's a shift on your horizontal. So you would multiply each x coordinate now by a. So you're basically replacing x by a times x. Oh, my apologies. This is, you'd be multiplying each x coordinate by 1 over a, not just a. Okay? So here we go. You end up stretching the graph of f horizontally if a is between 0 and 1, and you compress the graph of f horizontally if a is greater than 1. Okay. So now reflection about the x-axis. In the case where you have negative f of x, you reflect the graph of f about the x-axis. And what's happening in the function is you're multiplying f of x by -1. So each y value is opposite of what it started. And then if the negative's inside the function, you reflect the graph of f about the y-axis. And you're going to replace x by f at x, by -x. Okay, so here's a little practice. We've done some, whoops, not axis. We've looked at the pictures, so now let's look at these. And again, you can pause the movie if you want to try it on your own, or you can work along with me. So here we go. We're working with a graph of y equals x squared, but we want to write functions that have done these things. So A, shifted to the left 8 units. So that's a horizontal shift. So our f of x would be, remember, a shift to the left means you'd be adding 8, and the function is being squared. Shifting down, that's a vertical shift. So you would have your function squared, but each of them you'd subtract 8 from each y value. Reflected about the x-axis means that whatever was positive is now negative and vice versa, so it would be negative x squared. The negative is outside of what's being squared. And then, sorry, there's a typo here, shifted up 8 units, f at x would be x squared plus 8. Vertically compressed by a factor of 8. So we would have f of x would be equal to, so to compress it, it would be 1/8 of x squared. 1/8 of x squared. So each of your y values would be divided by 8. Okay, so horizontally stretched by a factor of 8 units. So this one is kind of odd. Since you do end up multiplying by 1 over a, we want to stretch this. So f at x would end up being 1/8 times x, the quantity squared. And that would give us a horizontal stretch by a factor of 8 units. Okay, shifted to the right 8 units, we would have f at x is equal to x minus 8, the quantity squared. And reflected about the y-axis would be f at x is equal to negative x, the quantity squared. All right, so now we're going to go ahead and graph each of these given functions using these techniques. So I gave you multiple grids to graph on so that we could, you draw your library function first and then you draw the different transformations successively. So here we go. Let's just call this one x and y. We'll just do our regular grid. Now this one will end up being x, h of x. It'll be our final graph. So the first one is going to be the graph of the library function. So y is root x. And then we'll do h of x. So y equal root x. Remember, you have ordered pairs at 0, 0, 1, 1, 4, 2, and 9, 3. So that's our graph of our library function. So now what we need to do is, if you're adding 1 within the function, that means you're shifting by 1 unit to the left. So instead of 0, 0, we'll be at negative 1, 0. Instead of 1, 1, we'll be at 0, 1, and so on. So instead of 4, 2, we'll be at 3, 2, and then at 8, 3. And so this is the final graph. So let's look at the domain and range for each of these. The domain for this one, 0 inclusive to infinity, as is the range. But this one was shifted 1 to the left, so the domain will change. It'll be negative 1 to infinity, but the range is still the same. All right? Good job. Okay, so now let's look at this guy. So again, our library function is going to be y equal to root x. So, and then this will be our final graph. So we just did this guy. Get the points in. So we have an ordered pair at 0, 0. So this is telling us to multiply each of your y values by 1/2. So my first one won't change. 0 times 1/2 is still 0. But this guy at 1, 1 will still have an input of 1, but it'll be at 1/2. And then we add 1, 2, 3, 4, 2. It'll now be at 4, 1. And then instead of 9, 3, it'll be at 9, 3/2. So this one has been vertically compressed. Put the scale on there. Okay, and then the domain and range will be the same for both. Okay, so now let's take a look at this guy. There's a couple things going on, right? We'll do our library function. We'll do our intermediate step where we do the reflection, and then we'll do the vertical shift last. So let's see what we've got going on here. My kitty. So for this one, we'll have x, and then y2 is root negative x. And then this will be our final. It'll be x, g at x. We'll do our regular grid, our scale. Okay, so again, we've done this one a few times. 0, 0, 1, 1, 4, 2, and then 9, 3. So that's our initial starting graph. So the domain and range for this guy, as we've done before, 0 to infinity, 0 inclusive. Now this guy we're going to be reflecting across the y-axis, so we'll still have a point at 0, 0, but we'll be reflecting about the y-axis. We'll have an ordered pair at negative 1, 1, and then negative 4, 2, and negative 9, 3. So this one's been reflected across the y-axis. So our domain changes. We still have 0, but it's over there, and we're going from minus infinity to 0. But do you see our range is still the same? Hasn't changed. Okay, so now we're going to work from the middle graph, and from each y value we're going to subtract 2. So there's a vertical shift where we're lowering the graph. So instead of an ordered pair at 0, 0, it'll be at 0, negative 2. And then instead of at negative 1, 1, it'll be at negative 1, negative 1. And then instead of at negative 4, 2, it'll be at negative 4, 0. And then instead of negative 9, 3, it'll be negative 9, 1. So it'll look something like this. Okay. So our domain on this one, it dropped down by 2, and it still goes up. Oop. Our domain didn't change. I was thinking of the range. So the domain is still going from minus infinity to 0. But our range changed. It dropped down by 2. So negative 2 to infinity is our range. And this is a useful way. It's kind of hard to graph them all on the same grid. It can get pretty confusing. So, all right, let's see what we've got. The greatest integer function of negative x. So again, we'll do our greatest integer function. So this will be x and y equals greatest integer function of just x. And then this will be x and h of x, which is our end result. Okay, so our greatest integer function graph, remember, went from 0 is included, has an output of 0, so all of these have outputs of 0. And we had done this in an earlier section, so I'm going to go kind of quick. Okay, so now let's take a look. So that's our integer function. We're supposed to reflect it across the the y-axis, because that negative is inside. So what's going to happen is, let's start at 0, 0. So this will still be the same, but the open circle is going to be on the left here, and it'll go like this. And then, so I just flipped that first one. So now if I flip this guy, I'll be here. So I'm flipping the next one over. So instead of having our open circles on the right side of each, they're going to be on the left side. And then we have these here. And you can see the reflection across that y-axis. So let's remember, this had kind of the strange range. The domain for each of these is going to be all real numbers, but the range is going to be the integers. So I'll just write it in set notation. You can go like dot, 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 -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. Basically, we want the set of integers. So this would be dot, 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 -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. Whoops. Okay, so now another kind of deep thinker question. Suppose that the function y equals f at x is decreasing on the interval from -2 to 7. So over what interval is the graph of f at x plus 2 decreasing? So when you're adding 2 within the function, it's a shift of 2 to the 2 to the left. So basically, you'd have to go from -4 to 5 to have the same behavior. Good so far? Okay, now same scenario, but now you've done a shift of 5 to the right. So you'd add 5 to each endpoint, and you would get 3 to 12. Now, what can be said about the graph of y equals negative f at x? Is it going to be increasing or decreasing? Good, it'll be increasing. If it had decreasing behavior and you reflect it across the x-axis, it's going to have increasing behavior. So it will be increasing on, and we only know about that interval from 2 to 7. Okay? All right, so that wraps up section 2.5. Don't forget to do some practice problems from the problem set, and I will be talking to you soon. Have a great day.